It looks like something an astronaut might feel at home in. And yes, it does fly. But technically speaking, it's still a boat. Once it reaches about 50 kilometres an hour, the airfoil Flareboat takes off and flies, just clear of the water. From the passenger seat, it's an incredible sensation in this two-seater version.
The airfoil Flareboat uses the principle of ground effect to generate lift and literally make it fly about 40 centimetres above the surface of the water. The great advantage of such a craft is its fuel efficiency. Because there is no resistance or drag from the hulls through the water, fuel savings of up to about 85% can be achieved. For a company operating these boats, that's a big saving. Okay, Ryan.
The 2, 4 and 9-seater versions are all capable of cruising at about 130 to 140 kilometres an hour. An air rudder at the rear is connected to the steering wheel to guide the craft. The lift is caused by air pressure between the water surface and the wings when the boat is moving forward. Former pilot and aeronautical engineer Gunther Jörg has 20 years and $2 million of his own money invested in the project. A huge 400-seat model is being planned that could operate in much rougher conditions over the open sea with a 2 to 3 metre flying capacity. But there'd obviously be a cut-off point where conditions would make such a boat unsafe. Further evaluation will answer those questions.
The Flareboat has 3 hulls. The centre compartment for both the smaller and the larger versions will always be used to carry passengers, while the 2 outer hulls act as stabilisers. Connecting the 3 hulls are 2 front and 2 rear aluminium wings. Once the boat reaches a certain speed, a delicate balance is struck between the weight of the craft and the lift generated by the ground effect. This ensures it will never flip over.
The principle of the airfoil Flareboat is tried and tested. Achieving high speeds with such low power has been a long-held goal of the marine industry. There's a strong possibility that the airfoil will be the next generation of high-speed water transport. Even that cliched line about leaving other boats in its wake is redundant. It doesn't produce a wake.
This has been a two-seater airfoil Flareboat flaring on the Rhine River. The next film is showing an 8-seater Flareboat over an Eastern German sea.
Frei.
that has been a short sequence out of first flights of the 8-seater. And now let's have a complete overview within the trailer. Oh, JPEG. I think we have to work without the trailer. You try to find it, very nice. There must be additional MPEG. Now we found it. There's just a few from helicopter, flying 4-seater on Lake Constance, flying 2-seater on the Main River, in harbor, just 4-seater on Lake Constance with increasing velocity. Drift around the mine. Stopping mode, acceleration, stopping mode, but just a quick stop, not a normal one. View from the top, part of the nose right rod. Thank you very much. Ladies and gentlemen, that have been the, I would say, most important film sequences to show the principle of and the function and the system. Now I try to explain some main components of the working system and to figure out the reasons for application as well as necessities for application system. This is a typical tandem airfoil flareboat shape. We have got following components. There are rear wings with additional elements on the back side. Front wings with front wings with additional elements on the back side, and rear wings all together are combined with some kind of lateral end discs over there, which are also called end plates. These parts are constructed as stringers and are connecting the wing tips. In the middle of the boat we have the fuselage consisting of cockpit, passenger unit, and additional luggage, or if there's a freight version, just luggage all over this place. There's a big room for storage. Empowered is a system by a whole power unit which consists of gas turbine or simply engine, propeller shaft, and propeller. There is no additional air screw or so on like we have with other systems, maybe hovercraft or so. That's all. The system is working, self-stabilizing, without pitch and roll controls. That's a schedule that shows the working of the stable ground effect flight. You've got the front wing section that has a higher lifting rate, and we have got the rear wing section over there, which controls the variabilities of the level flight. Both are carefully arranged to produce the aerodynamic stable ground effect flight. Stable. And that is the essence of all. We are real stable, own stable.
Natural.
Hmm?
Natural stability.
Natural stability. Thank you. Here we have a typical airfoil flareboat diagram about power of fuel consumption and speed. First of all, we have 3 different modes which each KAF flight passes: the swimming mode, the more gliding mode, and the flaring mode after take-off. If we look at this curve, we find out the fastest, the area of hydrostatic lifting needs a lot of fuel consumption up to a point of about 40% of total fuel consumption to a speed of 10%. Now there is the transition to the state of more hydrodynamic lifting. The fuel consumption decreases up to a relative minimum and decreases with more hydrodynamic lifting. Here's the top of fuel consumption at the transition from more hydrodynamic lifting to more aerodynamic lifting. And then we have a very much decrease of fuel consumption up to this point to take off. And this point is also the point of most efficiency. If you look at this sheet, there are 50% of speed with 30% of fuel consumption. Later on, we come back to this point because there are some applicational reasons where it behaves very well. This power or total weight in tons as function of velocity for different type of crafts. Here we find velocity, here's power, and we have this diagram shows the needed horsepower per weight in connection with speed for different kind of crafts. It is derived from the well-known Kármán diagram with additional tandem airfoil data. The TAF data are settled at the technical area for velocity between 100 kilometers and 200 kilometers an hour or even more, and needs an average horsepower per weight from 18 to 80 PS per ton, from here to at least here. This area can be enlarged by modern technologies and optimizing the system up to here. Now I've got no diagram, no additional, but I just like to talk. There's a problem about turning radii of TAF with 15 passengers. That's no problem, but the explanation. The essential points of applicability are acceleration, horsepower, velocity, deadweight, and safety. And the important question for WIGs, which are working in ground effect, is how to handle a flying or flaring object safely with turning conditions. The general problem with ground effect flights in turning condition is that due to the turning radii and flying mode, a flying object needs some more space. That's no problem if you are lifted higher in the air, but if you are near the water mirror, there could be, for instance, dangerous because of the following effect. One wing of an aircraft or WIG craft makes a movement towards the surface, while the other wing is extending space to the ground. And due to special characteristics of ground effect, the movement of one wing to the surface can lead to an uncontrolled lift of the contrary wing out of ground effect and thus trigger a non-intended effect of instability. TAF, Tandem Airfoil Flareboat, has solved this problem by special construction. The turning radius of a 50-seater, for example, in flaring mode is maximum 2,000 meters at a speed, and that must be stressed, at a speed of 150 kilometers an hour. This is to be compared with the speed of a car within the railway. Here we see the seaworthiness of high-speed ships. Modern vehicles that can be regarded as fast ferries are, for instance, semi-submersible catamaran, which is located here, air cushion catamaran. This one is this curve, hydrofoils, air cushion craft like hovercraft, and WIG boats over there, which are here located. Now let's explain the curves. The fastest ship among high-speed craft is a hovercraft, but only at flat seas. With increasing wave height, you have to throttle down the speed.
Why?
Because of water resistance?
Yes, but because for comfort or because you have not power?
Because of comfort.
Because of comfort.
Well, they have to slow down their speed up to a, well, let me say a middle a speed comparable with the one of a ship. Hydrofoils, which are located here, are very sensitive to choppy sea conditions, so they have to slow down their speed either. Seaworthiness is even better than the one of the hovercrafts. Semi-submersible catamarans, number 2, and air cushion catamarans, number 3, will behave stable even at higher waves. This curve is just following the one of the ship at a higher level. These boats are successfully concepts for ferries and passenger ships. Increasing wave heights cause a speed reduction even at full power. So, as conclusion, the application of fast ships is limited. Here we have number 6. Tandem Airfoil Flareboat. They are able to fly over the water level, following the waves high, only limited by a constructively defined maximum flying high. For each size of the craft. For instance, a 6 to 8 seater version has not the flying high, the same flying high as a 200 seater or a 400 seater over there. But in the essence, they have even better flying conditions than a ship or a hydrofoil or catamarans. Here we find the application possibilities in flaring and gliding mode for different sizes of TAF. These are just lines, but no deadlines, I would say, because there is a wide area and the handling is an important factor of flaring an airfoil flareboat. The limit at the moment we find a flaring high at 3 meters and a gliding high at 4.6 meters. Swimming is still unlimited. The measure for the TAF flight is an integrated average wave high. If you want to have some explanation thereafter, we can put it on the back of the lecture. In conclusion, is effective flying high in ground effect even more depending on handling, experience, payload, and air condition, and can be enlarged for each type. We've got some better experiences. the market is a very large one. You have got here the market shares for ships and boats, but it must be enlarged up to this somewhere, because the range of a ship or a boat is not limited. It must be something like this. We have, on the other hand, the area of the aircrafts, which need a minimum of takeoff speed, and range is limited by payload somewhere and by empowering. And here we have the area of airfoil flareboats or WIG crafts in general. Mr. Fischer showed some additional market chart too. We think it to be a very wide area because 1/7 of the Earth is only land and the rest is waterway.
With sea states.
With sea states.
Rough seas sometimes.
Well, doesn't matter. Oh. Now we've got some basics for implementation of a tandem airfoil flareboat line as fast ferry. First of all, we need the distance that has to be passed. We need the average wind and wave condition in the named area. You can have it from the geographical institutes or from consultings. You need the number of passengers to be transported. You need the wanted average speed and maximum speed. Then you have the fitting flareboat size. And you need the frequency of flights per day. Of course, you need financial planning and feasibility study and a time schedule. Some first point, distance that has to be passed, that is due to the customer, the range he wants to have. Point 2, average wind and wave conditions in the area. I just have example of installing a Baltic line in the Geographical Institute. Gave the information, and we have worked out that there are % of days where the wave height is maximum with this line. Wave height % of days, and this is Balticum and Northern Sea. And you can read that in 80% of the days, wave height is lower than 1.5 meters. Or, for instance, you find out if you like to have a ferry line which is working at 95% of the days, you must have an WIG craft that is able to pass the distance, in general, of 2.2 meters wave high. If you change the area and go to the Northern Sea, and you like to have 80% of the application possibilities, you need, according to the specialties of Northern Sea, at least 2.2 wave height that can be passed. with the example of, for instance, an 80-seater, we can work in 80% of all days at a wave height of at least 1.6 meters, or in 60% of days at wave height of 1.6 meters in Northern Sea. That's a very important kind of diagram, because it's directly showing the application possibilities of a craft.
What is Ostsee?
Balticum. Balticum. Baltic Sea. Baltic Sea, oh sorry.
Do you want this to use this one?
I later on I do it. Just put it here, thanks. This diagram is a very special one. It was scheduled for 80-seater and shows flaring high, fuel consumption, range, what's my point? Fuel consumption and range. You have to use it in a special way. Maybe you are interested in having 60% of the Baltic Sea with an 80-seater. For implementing this boat, kind of boat, you have got a empowering for takeoff of 4,660 horsepower. That means you are located here. A very essential thing is that we can and we must reduce the horsepower up to cruising speed. That means we can go to 2 engines. This 8-seater flareboat has 3 engines. We reduce to 2 engines, and we found here. When we are here, the range is still 1,250 kilometers at a flaring high of 1.5 meter in general. If we found out there's bad weather condition, you can add the 3rd engine, go higher with speed, and then you can pass even 2.3 meter, or at Vmax 2.5 meter. And this kind of diagram we found out for each boat.
230 kilometers per hour and a high of 2.5 meters.
230 kilometers an hour.
3 engines.
Okay,
This
sorry.
is for a given boat, a given TAF.
For a given TAF.
But for given TAFs, the number of engines change.
No, the engines are still there, but you zuschalten. We use it separately. That's just the point of reducing here. That means if you are just working with 2 engines, you find here, in general, 1.5 meter wave height passing at a fuel consumption of 330 kilogram per 100 kilometer. if you empower or if you if you go higher in speed, maybe you are here and find yourself at 2 meter wave height with V max somewhere between, no, with V somewhere between, and the fuel consumption somewhere here. That's it. And conclusion is, if we have an 80-seater flareboat, we have cruising power of about, no, you can leave it, 4,660 kV. You can reduce the power up to a minimum. You are still able to applicate in the wanted way. The range is fixed, and we have got a very, very good return on investment, and we figured out that could be 3.5 years. And as conclusion, we find out Tandem Airfoil Flareboat as self-stabilizing system should close the gap between ship and airplane. Thank you very much. Sorry for the delay in language.
Thank you, Dr. Ingrid Schellhaas. Thank you for your very clear explanation of your slides. I think that maybe there will be some question, not too much because we are somewhat late. Are there some questions from the floor?
Well, my name is Alan Bonnet. I have one question. At the moment, it was some reference with ecological means. And aren't you afraid with birds that you can, for example, on the rivers and so on? Because we know that the speed is a problem, you know, with airplanes. No problem?
You have got different modes. You can speed, you have got the shipping mode, the gliding mode, and the flaring mode. And in flaring mode, you have got very small turning radius, very short brake distances, and we are able to react very
rapidly,
almost immediately.
Okay.
Of course, you have to take good care of the other.
Of course.
Hast du da noch was dazu sagen?
Une question?
Jean-Gaël from Eurovia Toulouse. Well, it's just the following question. How long is the braking distance, for example, at 100 kilometers per hour?
How long is the braking distance?
For 100
50 meters
per
or
hour
so.
or
50 meters or so with a small boat, a little bit more with a bigger boat.
less than 100 meters.
You just can compare this with a motorbike or with a car. It's even the same in handling. We have just got the steering wheel and throttle. No? Throttle?
Yes, that's all.
That's all.
Thank you.
You have a turning radius very
Speak loud.
200 meters.
Thank. I'm Mats Larsson from Stockholm. As I understand, the main feat of this double airfoil is stability. What do you pay extra for this stability? Is there some extra motor power or some in percentage, for instance?
Stability is arranged by the shape and the profile and a special arrangement. It has nothing to do with empowering ourselves.
But if you compare with other flare boat with just one airfoil and a stabilizer, do you need extra power, so to speak?
Well, that's what we don't have. You must know, in the year 1964, there have been first arithmetics to this theme, and we started the research with computer-added profiles. It was a very special thing because Mr. Jörg had to write the program for himself. It was not like nowadays.
No. Thank you very much.
Simple conditions.
One more question, if there is a question, one more only. Mr. Fischer, no? No question? Okay. So, thank you very much again to Dr. Jörg and the daughter of Dr. Jörg, Dr. Jörg. Thank you. So.